Picture a fleet of web servers all serving the same site. A customer uploads a photo on one machine. Moments later, another machine tries to show that photo and finds nothing. The file only lived on the first server's private disk. That is the quiet crisis behind modern cloud apps. One machine's disk is no longer enough when many machines must read and write the same files. Training an AI model on a shared dataset, rendering a film across a render farm, hosting WordPress across a fleet. Copy the data everywhere and you drown in drift, cost, and inconsistency. Keep it on one box and you create a single point of failure. Amazon Elastic Block Store, EBS, behaves like a private virtual hard drive, fast, familiar, usually attached to one instance. Amazon S3 is a vast object warehouse reached through an API, not a normal folder. So the question hangs in the air. How can many machines work on one ordinary looking folder without copying it everywhere, and without losing reliability when a zone fails? Amazon Elastic File System, EFS, was built for exactly that gap. It is fully managed, serverless, elastic file storage. You do not provision capacity in advance. The file system grows and shrinks as you add or delete files. Under the hood, it speaks NFS version 4, the same network file system protocol Linux has used for decades. To your application, it looks like a mounted directory. Ordinary open, read, write, and lock calls. No special object API. No rewriting the app to speak REST. Thousands of compute resources can attach at once. EC2 virtual machines, containers on ECS or EKS, even Lambda functions. And unlike a lonely EBS volume stuck in one place, EFS is regional. It automatically replicates data across multiple availability zones inside a region. So a single zone outage does not erase the shared shelf. Think of it as one library many readers can visit at the same time, instead of every reader carrying a private photocopy that slowly goes out of date. But a shared folder is only useful if the machines can actually reach it. Here is how the folder crosses the network. First, there is the file system itself, the top-level shared storage resource in a region. Then come mount targets. You place a mount target in a VPC subnet in each availability zone you care about. Each mount target gets an IP address that clients can dial. Clients, your EC2 instances, containers, functions, sit in the same VPC. They open an NFS connection to a nearby mount target. Traffic stays inside the private network. AWS keeps the data durable across zones while your app simply sees a path like /mnt/EFS. The source diagram walks the journey. Connect compute to EFS, mount, test, and optimize, move data in, then share and protect it. The clever part is what you do not manage. No RAID arrays, no NFS server VMs to patch, no capacity planning spreadsheets. Still, none of that works until security groups and mount commands line up. So let's walk the real setup, step by step. Step 1. In the AWS console, you create an EFS file system and choose the target VPC. AWS spins up the regional resource and the mount targets. Step 2. Launch one or more EC2 instances in that same VPC. Same network neighborhood, that matters. Step 3. Open the door carefully. Update the EFS security group to allow inbound traffic on port 2049, the NFS port, and only from the security group attached to your trusted clients. Not from the whole internet, just from the machines that should share the folder. Step 4. On each Linux instance, mount with the EFS mount helper. A typical command uses TLS, points at the file system ID, and lands on a local directory. From that moment, the path behaves like any other folder. Write a file from instance A, instance B sees it almost instantly, and can write back. That is the payoff. One namespace, many writers, no manual sync scripts. Once everyone can read the same shelf, though, traffic, not empty disk space, may become the new bottleneck. 3 storage models now compete for your architecture diagram. Personify them, and the choice gets clearer. EBS is the fast private disk, block storage, ultra-low latency. It can boot an operating system, usually one instance at a time. Think of it as the laptop drive under your desk, blazing for one owner, useless as a shared team drive. EFS is the shared Linux file cabinet, file storage over NFS. Many instances mount it together. Latency is low, but higher than local EBS because every byte crosses the network. It will not boot your OS. Petabyte scale capacity. Indicative pricing in the source sits higher per gigabyte month than cold object storage, roughly 30 cents versus pennies on S3, because you are buying a living file system, not a blob warehouse. S3 is the vast object warehouse. You address objects through a REST API. Enormous durability and scale, on the order of 10 to the power of 12 times a 50 gig object in the comparison table. Latency is higher. You redesign apps to speak object, not POSIX files. EFS wins when the problem is simultaneous file access with familiar Linux semantics. It does not automatically win on raw speed or lowest bill. Sharing solves coordination, not every workload's speed requirement. When sharing gets busy, two dials matter: performance mode and throughput mode. Performance mode first. General purpose is the default, lowest latency per operation. Ideal for web serving, content management, general file shares. It supports up to 35,000 read IOPS and 7,000 write IOPS. Watch the percent IO limit metric in CloudWatch. When you push past those ceilings, max IO is the scale out option. Higher aggregate throughput across thousands of parallel connections at the cost of slightly higher latency per operation. One zone storage classes only support general purpose. Throughput mode is the second dial. Elastic automatically adjusts on demand to match active workload, the modern recommended default for spiky traffic. Bursting ties baseline throughput to how much data you store, with burst credits scaling up to about 100 megabytes per second per tebibyte. Provisioned guarantees a constant megabytes per second floor, whether your disk is nearly empty or full. Useful for steady pipelines that must never stall. A quiet brochure site can live happily on general purpose with elastic or bursting. A parallel analytics job that hammers metadata may need max I/O. A predictable media pipeline may buy provisioned so render nodes never wait on credit recovery. The cheapest configuration is not always the one that finishes the job on time. Cost is where convenience can turn expensive, or surprisingly thrifty. EFS offers storage classes. Standard keeps active data on high-performance media. Standard infrequent access, standard IA, holds files you touch less often at a lower per gigabyte rate. There are also one zone and one zone IA variants when you accept single AZ risk for a lower price. Lifecycle policies act like a careful warehouse clerk. After a file sits untouched for a threshold, 30 days is a common setting, EFS can transition it into infrequent access automatically. The source notes that aggressive lifecycle use can cut storage costs by up to 92%. Reads and transitions on IA tiers carry request charges, so the clerk is not free. But for cold training checkpoints or old media masters, the math often wins. Pricing has three main dimensions: which storage tier holds the bytes, which throughput mode you chose, elastic bills work done, provisioned bills reserved megabytes per second, and IA access or transition requests. Spend where the workload is hot. Archive where it sleeps. That is the economic half of shared storage. Walk 3 concrete workloads through the dials, the way an on-call engineer would. Workload 1, a modest WordPress fleet. Traffic is chatty but not extreme. Metadata ops matter more than bulk streaming. General purpose performance mode. Elastic throughput, so a launch day spike does not require a ticket to raise provisioned megabytes. Lifecycle policy moves last month's unused uploads toward infrequent access. Security group locked to the web tier only. Workload 2, a nightly analytics sweep. Thousands of parallel readers hammer small files. General purpose hits its IOPS critical ceiling. CloudWatch %IO limit climbs. You switch the file system toward max IO so aggregate throughput can climb across the farm, accepting a bit more latency per call. Bursting may suffice if the dataset is large enough to fund credits. Otherwise, Elastic keeps the night job from stalling. Workload 3, a media render pipeline with a known floor. Artists need steady ingest. Provisioned throughput buys a guaranteed megabytes per second baseline even when the project folder is still small. Standard class for active timelines. Older completed shots age into IA after 30 quiet days. Up to that 92% storage saving the source cites, while hot working sets stay fast. Same service, 3 different truth tables. The mistake is treating EFS as one knob labeled on. The craft is matching mode, class, and policy to the shape of the traffic. Shared shelves need locks on the doors. Security is layered. Security groups must allow NFS port 2049 only from trusted client groups. IAM policies govern who may mount and whether root level privileges are allowed. KMS managed keys encrypt data at rest. TLS mount options encrypt data in transit so packets crossing the VPC are not readable in the clear. AWS Backup integrates for automated point-in-time recovery. And because EFS speaks POSIX permissions and semantics, Linux applications keep the file modes and ownership models they already understand. Where does this pattern shine in the real world? Secure file sharing across a team of instances. Fleet-based web hosting, classic WordPress content on a shared document root. Machine learning and AI training where many workers stream the same dataset in parallel. Big data analytics jobs that need scale-on-demand throughput. Media processing and rendering farms chewing through high bitrate mezzanine files. In each story, the hero is the same. One coherent file namespace instead of a brittle tree of copies. Convenience, though, always has a price, and a list of things EFS will not pretend to be. Name the limits honestly so the architecture stays honest. EFS is primarily for Linux workloads using NFS. It is not a native Windows file service. Because it is network-based, latency sits above local EBS, fine for shared content, painful if you expected bare metal disk speed. A single file may be at most about 47.9 tebibytes. At large scale, the bill can exceed EBS or S3 for the same raw gigabytes. And while multi-AZ replication inside a region is automatic, cross-region replication can add latency when you stretch the design across the planet. Advantages on the other side of the ledger: automatic elasticity, true parallel access, multi-AZ durability inside the region, backup integration, and POSIX compatibility that lets legacy Linux apps mount and go. So what did the shared folder make possible? Web fleets, training clusters, analytics jobs, and media pipelines can coordinate through one elastic file namespace rather than maintaining isolated copies that drift apart. The opening crisis, a photo uploaded on one server invisible to the next, has a managed answer. The field is still chasing the harder balance. How should distributed storage continuously trade instant shared access, regional resilience, performance, and cost as workloads cross regions and outgrow today's assumptions? That question does not end when the mount succeeds. It begins there.